I love this idea, thinking about how an experiment helps us determine between competing theories, because it really cuts to the heart of what it is to be a physicist, what it is to be a scientist. So on one hand, we've got the ether model for the transmission of light, and on the other hand, we have, well, for the want of a better name for the moment, let's call it Einstein's model for the transmission of light. And let's have a look at some of the differences between them. So here we are with our two theories, our ether model for the transmission of light, which is a really nice, comfortable model. It's based upon what we think the world would be like. Light's a wave, therefore it has to have a medium because every other wave has a medium. And out of that comes this consequence that we should be able to measure the speed of the Earth relative to the ether. On the other hand, we've got Einstein's bizarre model. It's based upon a seemingly harmless statement that everyone's going to measure the speed of light as the same if they're in an inertial frame of reference. That way he's preserved relativity, but out of that comes these bizarre predictions that space and time are relative. The very bedrocks of our universe, the things that we thought we build our universe on, are actually relative to the frame of reference that you're in. So weird things happen, time dilates, length contracts, mass dilates, and in fact out of relativity comes Einstein's famous experiment, E equals mc squared. Now, of course, sitting in the middle of all of this, as the dot point wants us to think about, is the Michelson-Morley experiment. Now, Michelson and Morley never set up the experiment to determine between these two theories. They set up the experiment because they completely believed the ether model. They were simply just trying to measure the speed of the Earth relative to the ether. But the problem is they got a null result. No matter how many times they tried to measure it, they got no result. Now, it could be that the Earth could be travelling with the ether for a period of time, but if you wait 6 months, then we have to be travelling against the ether, and in fact that's what they did. Not only that, but their experiment was well and truly sensitive enough to be able to measure the speed of the Earth relative to the ether. Now, on the other hand here, we've got Einstein's theory, and implicit in Einstein's theory is no ether. Because if there is an ether, you can't have C being constant for all observers. So Einstein's model doesn't need an ether. In fact, it has to have no ether at all. So Michelson-Morley's experiment sits in the middle here, and it really comes down to, are we going to go with a theory that we're comfortable with, that fits the way we want the world to be, or are we going to move to a theory that's weird and strange and has these amazing predictions, but actually better fits the data? Now, of course, many, many years after the Michelson-Morley experiment, there's been lots of experiments done to show that time does actually dilate, length contracts. Every nuclear power station in the world runs on the idea that E equals mc squared, the mass defect. In fact, our GPS system that we use to navigate has to take into account some of the effects that came out of Einstein's model for light. So on one hand, we've got a theory which is nice, but doesn't fit the evidence. On the other hand, we've got a theory that's a little bit confronting, that's going to challenge us, but better meets the evidence. And here's the joy, here's the essence of what it is to be a physicist, what it is to be a scientist, is that ultimately, while theory guides, as the saying goes, evidence decides. And ultimately, it was the Michelson-Morley's data, their null result, that allowed for us to put some support behind Einstein's model for the transmission of light and develop that further.